Hello everyone. We discussed contest 8. So I expect it to be easier actually, but probably the first problem is a little bit too much for some of you. So some people spend half an hour solving first problem. That's not what expected actually, but overall solved pretty good. So a lot of people solved those problems like the last time. So good results. Let's discuss that. So maybe a little bit too large gap between problem 4 problem 5, maybe a little bit too much. We'll see. So let's discuss the problems. Okay, so first problem may be a little bit too difficult for you. So what we have in the first problem, we have some number of cards. We need to divide them into pairs in such a way that sum of cards in each pair is the same. So first let's discuss the problem example. So let's see here. So we have here what we have: 1, 5, 7, 4, 4, and 3. And we split them like here. So these numbers are indices of the cards. So indices 1, 2, 3, 4, 5, 6. So we take cards 1 and 3. It's this card and this card. So we have 1 plus 7. Yeah. This, sorry. 7. Okay. This one and this one. Then we take cards 6 and 2. 6 is 3 and 2 is 5. We have 3 plus 5. And then we characterize 4 and 5, these two. Yeah. 4 plus 4. And we see that all these sums equal to 8. Okay, if you just want to solve this task, you have cards and you need to split them into groups with the same sum. Well, how do you usually do? Again, let's take the minimal card. So how you think when you solve problems like this? You think, okay, let's start from something. You can start from minimal card, from maximal card, and then kind of try to figure out what you need to do. So if you take the minimal card and you want all sums be the same, then if you take the minimal card, you kind of want to pair it with some big cards. So all the sums are the same. Yeah. Again, you have some sum that one pair that has minimal card and another sum that has maximal card. And again, so imagine you have one card is very small, another card is very large. Yeah. If you put them in different pairs, so you have small card and something, and then you have something and large card. Yeah. Then this sum will be obviously bigger than this sum. Once again, so if you pick the smallest card and the largest card, and look at the pairs, yeah. So the smallest card is in one pair, biggest card is in another pair. So if they are two different pairs, then this pair will have bigger sum than this pair. Yeah. The only way you can make these pairs have equal sum is put them in the same pair. So if you have the smallest card, you need to pair it with the maximal, the largest card. Yeah. So if you find the maximum in minimum card, they should be in the same pair. If they're in different pairs, then pair with maximal card will have bigger sum than pair with minimal sum. And you just continue. So again, we did something that's called safe step in greedy algorithms terms. So we try to construct the solution. We make one step which we are we're sure this step must be made. So if we're sure that the minimal card should be paired with the maximal card, we can then remove these two cards from the set and continue the process again. Yeah? So what will happen? So imagine you have all these cards. Let's sort them. So you take the minimal card and maximal card and move them in the same pair. Now you remove them from the set and you need to repeat the same process again. Now in the remaining set you have a minimal card and the maximal card. And again, by the same reasoning, you need to put them in the same pair and so on. So that's how you assign all pairs to all cards. Again, this picture is kind of intuitively correct. Yeah. So if you just think about it a little bit about this problem, that's how you make pairs of equal sums. You take small cards, big cards, and the smallest the smaller is the first element. The bigger should be the next element. So good. So that's what we implement. So how to implement this? The problem in this here is why it's technically a little bit more difficult because of the output. So we need to output the indices of these cards. So we need to sort this card, but remember the indices. Let's try to implement this. So what we do? Can you please let me slow? I'm trying. It's actually this one of the slowest mode I have. I will try to do it even slower, but sorry. I usually try to slow down as much as I can, but again, if it is sometimes I fail. So if it is too fast, just tell me, okay? So what we will do, let's read all this data first. I can type even faster than I speak, actually. Like this. So now I need to sort this array, but remember the indices of these elements. Yeah. So for each element, I want to remember what is the index of this element in this initial array. Yeah. Because I need to output these indices here. So what I will do, the easiest way to do it is like this. So let's make another array of pairs. B. And I will put pairs of element and its index. So I'll do it like this. I will put pair of element and index of this element. Now, I will just sort this array of pairs. So instead of sorting my initial array, if I just sort my initial array, I will lose all initial indices. Yeah? But here I will store these indices. So for every element, I know its index. Yeah? So I can just sort this array. And now for each element, I will remember its index. So let's just print all of them. First. Second. Like this. Other way. So you see, so here's what we got. So again, I create array of pairs. For every element, I remember index of this element. And now I sort these pairs. If you sort array of pairs, you will sort them by the first element. And if first element is the same, by the second element. So it's kind of like lexicographically sort. You sort by the first element. If the first element is equal, then you sort by the second element. In my case, all elements are different, so I will just, so these two are the same. So yes, so I will sort all elements. Again, important thing, I will sort all elements by the first element, all pairs by the first element. First element is just the value in my array A. Yes, so I take these values here. So here, the first column here is the sorted array A. Yeah? I take all these values and sort them. Second column is column of indices. So for every element, I kind of glue index to this element. Yeah, so I take element plus index. Yeah, so I put them together in a pair and then sort these pairs. So I don't forget these indices. And now I know the indices of all elements in sorted order. Now I just need to take the elements like this. You take the first element, pair with the last element. Take the second element, pair of this element, and so on. Yeah? So let's do it like this. So we have n over 2 pairs. So we need element of index I plus 1. Plus 1 because we have indices from 1 in the problem, but my internal indices are from 0. Yeah? So to get from these indices to this index, I need to get plus 1. Yeah? So we get element I and element, so you need element with index I from the end. Yeah, the last index is n minus 1. Yeah, so you need index n minus 1 minus I. Yeah, so this is how you get index I from the end. So here, this is the end. Yes, so you get n minus I. Yeah, second plus 1. That's all. Again, nothing actually that difficult, but still you need to sum. So I believe that idea of the problem is of solution is really easy. So the idea is like you combine small element with large element to get all the equal sums. Implementation is a little bit maybe too difficult for the first problem of the contest because you need to maintain analysis. So maybe a little bit too much for the first problem of the contest, but still nothing really that difficult. So it's just you need to sort the array, maintaining the indices. That's the easiest way to do it is do it like this. There are other ways to do it. You can sort the elements with comparator based analysis. It's also possible. We will not do it today. Let's keep it simple. So this is the most simple way to sort the array and maintain the indices of all elements. So what we have in problem B? We have a long story about some bear who trades the honey for some raspberries. Okay, so it's kind of strange story, but what you need to do is just read it and understand what the authors tried to tell you. And they try to tell something like this. So we have array of prices. So for every day we have price of the honey in kilograms of raspberries. Yes. So we know how much costs the barrel of honey in kilograms of raspberries. Doesn't matter. So we have some item and we have a prices of this item. Yeah. So we have the prices of the item. And now you need to carefully understand what you can do. You can do the following things. So you can borrow this barrel of honey in some day, then sell it, and then the next day you buy it again. So it's not like typically you do something like this when you wanna get money in some market. You buy something cheap, then sell it when it's expensive. Yes. Here you do something in reverse. It's actually how it's happening in the real markets. You borrow something, sell it, then buy it again, and then return. Yeah, that's how you get money when something then the price goes down. Now what we ask you now let's carefully understand what they ask you. So we need to execute this plan only once. So we need to find one place in this timeline when we borrow the barrel, sell it, then buy it. Then they also pay amount of C. Where is it? Yes, we pay this price for borrowing this barrel, and we need to calculate the maximal income we can get from this situation. So again, what we need to do? We need to find the best place. Okay, what is the freedom? What can we choose? We can choose when execute this plan. So the plan is like this: we borrow the barrel, we sell it, then we buy it back, and pay these C kilograms as a reward. Yeah, and we need to find the place to do it optimally. So we need to find the place when we need to sell, when we need to buy, to maximize our income. That's all. Again, how we do it? No, we just carefully look at every place when we can do so. If we sell it again, if we execute this plan in time, so if we execute this plan in time A, then the price. So first we sell the barrel. So when we sell, we get xi amount of raspberry. Yeah. Then we need to buy it again. So we lose this amount. Yeah. So when we sell, we get money. When we buy, we lose money. Yeah. So we get this amount of money, lose this amount of money, and also we pay this amount of money for borrowing this barrel. Yeah. So this is our income. So we need to maximize this number for all values of I. That's all. Let's implement just like this. Again. Now, I'll just check all possible points of time, moments of time when I execute this plan. So I will do for I from 0 to n minus 1. I do it to n minus 1 because I need two points. I have I and I plus 1, yeah? So there are n minus 1 possible positions. So what my income will be, so let's put it in some value w. Will be, again, it will be xi minus xi plus 1 and minus c. I will need to read c. And now, over all these possible cases, I need to find the maximal one. So I'll need result 0. Result will equal 0. I always can do nothing and get 0. And just update my result. Looks fine. Let's try it. So this is the whole code, basically. Again, problem is scary. Statement is pretty long, but solution itself is pretty easy. So no tricks here. Just need to implement what's written in the problem statement. Another fun problem. So we need to reconstruct the magic square. We need to reconstruct the magic square, then the numbers on the main diagonal are missed. So we're missing with these three numbers on the main diagonal. We need to reconstruct the magic square. That's it. That's the whole problem. Let's consider the second example. It's a little more interesting than the first one. So. So imagine I have something, have 3, 6, 5, so something here, 5, and 4, 7, something. Now, you kind of need to guess all three numbers, yes? So what you can do 3 loops and try to guess all 3 numbers and check if the result is correct magic square. But it's actually too much. So imagine you guessed one of the numbers. So imagine you put this number, for example. So imagine you put here number, I don't know, 1 in this position. Yeah. Then we know that the sum in this row is 1 plus 3 plus 6, so it is 10. Yeah. So sum in this line also should be 10. Yeah. But we already have 5 and 5. So we know that the middle number must be 0. Yeah? It's the only way how can we get sum equal to 10. The same for the first line, for the third line. So we need sum be equal to 10, but numbers are already 4 and 7. Then we know that this number must be minus 1. So we fix one of the numbers, and we immediately know which numbers we need to put. It's actually quite similar to the problems we solved few contests before. It was even harder, I believe, last time. So again, you need to guess few numbers, but when you fix one number, you immediately can calculate all other numbers. So instead of trying to check all possible combinations of 3 numbers, you just pick one number and just calculate all other numbers. Now, what we need to calculate actually? So we need to build a square such that all numbers are positive and not exceeding the 10 power 5. So we need all numbers be in region from 1 to 10 power 5. So if you put 1, it will be not good. So these numbers are less than 1. But what you can do, you can put number, for example, 5 here. If you put 5 here, then you will need to calculate 4 here, calculate 3 here, because the sum is 8 plus 6, 14. So, again, there are 2 ways to solve this problem. Because numbers are small, up to 10 power 5, you can just iterate for all numbers here. So I put number x in this position. And I immediately can calculate these two numbers. I just check if they both are in region from 1 to 10 power 5. And if it is true, I just output and I'm done. Another way is to intersect the segments. We did exactly the same. I will not repeat it. We did exactly the same few contests before. So you can calculate the numbers, so numbers here and here. So if you calculate number x here, you can immediately calculate this. So if you put number x here, you can see that the sum should be equal x plus 9. Yeah. So here is 10. So this number should be x plus 9 minus 10 should be x minus 1. And this number should be x minus 2. So then you have in equations like x should be in region from 1 to 10 power 5. Then you have x minus 1 should be in region from 1 to 10 power 5. And x minus 2 should be in the same region, yes. But if x minus 1 is in the region, so it is the same as if x, so you just put this minus 1 here, yeah. So it should be from 2 to 10 power 5 plus 1. So you have some number of segments here. So x should belong to this segment, x should belong to this segment. You just intersect all the segments and print any element in this intersection. So two possible solutions. So let's implement the easiest one. Okay, how we solve? Do we need 9 variables? What do you prefer? I would prefer to have two-dimensional array actually. Well, I'll just read them as you normally read arrays. Not my usual keyboard. I miss keys every time. Now, let's iterate our element we put in the top left corner. So we'll have x from 1 to 10 power 5. 1, 2, 3, 4, 5. Now we check if they put. Okay, let me put back there. So if we put element x here, then our sum will be x plus element a01 plus element m02. Okay. Now we can calculate all other elements. So we calculate next element. Well, let's actually put it like a0 e0 equal x. I'll just put them in the same array. Now element 1 1 should be s minus a10 minus a12, and element 2 2 must be s minus a20 minus a21. Do they guarantee that it always exists? Yes, they guarantee it exists. Okay, so we don't need to check everything. That's all. And now we just check. So we check if a11 is at least 1, if a11 is at more than 10 power 5. I would put it a constant, but not today. And a22 is at least 1. So if I have more than 2 times, I will probably put them in a constant. But if you just need to repeat it twice, I will keep it like this. So if it is good, then I will just output the result. Let's just break. And then here I'll output the result. Oh, that's it. So again, you read the input, you check all possible values for the top left corner, for this corner. Yeah? Calculate all other elements. Vector is just a matrix. Yes, it's just a matrix. You can do that like this instead. Also over. I just prefer vectors always. So when I don't know what to do, I use vectors. So I use vectors until I have time limits, some strange time limits. When I need to optimize time very hard, then I probably will move to arrays. But before that, I will use arrays always. I will use vectors always. That's all. Let's check. Oh, copy. Looks okay. Any questions? No? Wrong answer test 2. Okay, why? Ah, and diagonals. Okay, you need to check also diagonals. I forgot. Okay. Okay, let's check diagonals also. Okay. And you also need to check that A00 plus A11 plus A22 equals to S. Okay, you also need to check the other diagonal, but it will be all right actually, so I will not do it. If you check this diagonal, it automatically will mean that all other diagonals are also the same. Okay. Just you need to be more careful when you read in this statement. Okay, I just missed one part of the statement and got wrong answer. That's it. So again, not easy problem. You need to think. You need to implement. It's actually again like 40 lines of code. So it's quite sparse, but again, you need to implement something. Not the easiest problem, but still quite approachable. So don't be scared of problems like this. It looks scary. So you have some metrics. You need to find some magic squares. It sounds very scary, but problem itself is not really scary. Just problem statement is scary. It happens. So problem statement is scary, but the solution is not scary. Oh, problem D is nice, easy problem actually. So what we need in problem D, we need to we have array, and we need to find all the elements that equal to the average of all other elements. So arithmetic mean is just sum divided by number of elements. Like in this, if we take a number 3, it will be equal to the average of all other numbers of 1, 2, 4, and 5. Okay, let's write the formulas. So here I have element 1, 2, 3, 4, and 5. Yeah. If you look elements 1, 2, 4, and 5, the arithmetic mean will be 1 plus 2 plus 4 plus 5 divided by number of elements. Number of elements is 4. Yeah. So it will be 3, 7, 12 divided by 4 equal to 3. Yeah. And so my middle element equals to the arithmetic mean of all other elements. First, let's implement it like it is here. So I'll just tell you what's happening. I think it's easy to implement it and then look at it. So let's just implement it like it is, and then we'll just upgrade this code. Let's just do it like I told you. I will just check that the element equals to this. Right? So what we do? We pick the element. Now we calculate the average of all other elements. How we do it? We calculate sum of all other elements. So I'll just do it like this. So if j is not I will add this element. So this is sum of all elements except I. Yeah? Now I'll check if my element equals to this sum divided by number of other elements. So it's not correct code. We will fix it. Yeah? Yeah? Then it's okay. Yeah? So it's okay. It means I need to output it. I need to output indices. Okay. So let's save them somewhere. Yeah, just yeah. And in the end, just output size and then all elements, right? plus 1 also, because or something like this. Yeah. Okay. Not really. Okay, what we're missing? J, of course. Yeah. So if you sum elements equal to AI, then the average will be equal to AI. It kind of makes sense. Yes. Okay, so it kind of looks kind of okay. So now let's just fix all the problems of this code. Okay, so again, sometimes it's better to start from something simple. So try to some simple solution, and then then just improve it until you have the correct solution. So this solution is not correct. What will happen if I submit it? What do you think? What's your prediction? I predict wrong answer test number 2. Time limit. Okay. Okay. So let's fix this problem first. Let's fix this problem first. So why we have time limit? Because the array is quite large. So size of the array is 2 by 10 power 5. So we have 200,000 elements. And this solution has quadratic time complexity. Yes, I have one loop, another loop. Yeah, both loops of 10 power 9. So it's 10 power 10. It's too much. Yeah, for 1 second it will not fit. Yeah. So what we'll do? Let's improve. Let's fix this problem first. So how can I improve time complexity? No, let's fix. What is the bottleneck of this problem? Bottleneck is this calculating the sum of all elements except one. But if you think about it, how you calculate sum of all elements except one? No, it's easy. You take sum of all elements and then remove one. Yeah. And to do this, you need to calculate the sum of all elements only once. So you calculate the sum of all elements before. So S is just sum of all elements. And here you just take sum of all elements minus your element. So now I have linear time solution. So I have one loop here, one loop here. Very simple linear time solution. Let's check it still works. Yeah. Let's submit it again. Okay, now I hope we will have a wrong answer finally. 15. Okay, close. Why we have wrong answer? No, because of this division actually. So every time every time you see division in your code, just think about, just stop and think what I'm dividing and what I plan to achieve when I divide something. So here, so what happens when you divide? No, many bad things may happen. First of all, you may divide by 0. Let's check if it doesn't happen. No, it doesn't happen because it will you will have average of empty set. So n is at least 2. So this part is not 0. Okay. So at least we don't have this problem. So we never divide by 0. What other problem we have here? So we divide integer by integer. Yeah. So sometimes when you divide integer by integer, you have non-integer result. Yeah, it may happen. So when I divide this by this, it may happen that it's not divisible. Yeah. What will happen then? I will have the wrong answer. So I have something which is not divisible. When I divide it in integers, I will just drop the remainder. That's not what I will plan to do. I need to have exactly like this. So there are two options. What you can do. You can check if it is divisible. Let's check. You may check if this modulo this equals to 0 and. So here I check if one integer is actually divisible by another integer and the result of this division equals to my number. That's one way to fix it. It will fix, I don't know. I believe no more problems in this code actually, so let's submit it. So that's one way to fix it. Another way to fix it is actually more natural for me, but again, it's if you just start doing it, so maybe a little bit tricky, but try to avoid divisions at all. So try to use divisions only when you actually need them. In this problem, I don't need them. So what I need to do? I need to check that one number is another number. So let's write it here. So imagine you need to check that x equals to y divided by z. Yeah. So instead of checking this, I will move this z to the left and check that x multiplied by z equals to y. Yeah. And in this check, I don't need any divisions. The good thing, it also works when you have when you compare two fractions, like if you have a divided by b equals to c divided by d, something like this. So you multiply everything by b and by d, and it is the same as a multiplied by d equals to c multiplied by b. So instead of divisions, you just multiply. So how I will apply it here? I will check that this multiply by n minus 1 equals to this. Now, every time you write multiplication, you check that you don't have integer overflow problems. Let's check. No, I remember I don't have them, but let's check. So AI is up to 1000. This is up to 10 power 5. Yeah. So this product is up to 10 power 8. Should fit in normal integers, 32 bits. Yes. So here fine. I don't have integer overflow problems here. So this is another solution to this division problem. So you don't need to divide. You just need to multiply. And if it's not divisible, you just have false in this problem. That's all. There's two solutions to this problem for you. So problem E. In problem E, we have a long string like this, and we need to split it into parts such way that every part is a correct file name. Correct file name means it is formed like this. So we have name, dot, then extension. Name should be a string of length from 1 to 8 characters, and extension should be a string of form of from 1 to 3 characters. That's all. That's the whole problem. Now, again, if you play a little bit with this system, what we will have? So you have this input line, yeah? So it contains some strings divided by dots. These dots. Now, when you split this line into parts, you always split somewhere here in the middle. So every part should contain exactly one dot. Yeah. So you split only in between these dots. Let's write it. So you have your line. So you have something dot something dot something dot something. Yeah. So when you split this line into parts, you always split in such a way that every part contains exactly one dot. So you split somewhere here, and so on. So you achieve this part, and this part. Now, let's look. So this first part before the first dot should be in the first file name. So it must have length from 1 to 8. This last part should be extension of the last file name. Yeah? So it must have length from 1 to 3. Now, every middle part should be concatenation of some file name and some extension and some file name. So this part has length from 1 to 3, and this part has length from 1 to 8. Yeah? If you combine them, you can get any length from 2, yeah? And maximum length is 11. Yeah? So now let's think, if I have a string of size from 2 to 11, is it always possible to split it into two parts like this? Well, yes, you can say that it's always possible. If you have of line 2, okay, let's take 2. You split it as 1 plus 1. If you have 3, split it as let's say 1 plus 2. Of side 4, you split it to 1 plus 4, right? Plus 3, and so on. You do it up to 9 equals 1 plus 8. Then you cannot extend this more. So when you go to 10, you extend it to 2 plus 8, 11 as 3 plus 8. So for every length from 2 to 11, I can split it into parts in such a way the first part is from 1 to 3, second is from 1 to 8. And that's it, that's the whole solution. So I'll just check this, find these points when I need to split, and output. Now implementation part, that's a little bit more complicated. So now we need we need to implement all this stuff. Let's do it. First, we need to split this string into parts by these dots. Probably C++ have a function for this. I'm not sure. I'm not good at C++. So instead of looking for the function, I will just implement my own. So we'll have vector of string parts. Let's see P. Let's just char C of this. String, let's say core. So this is my current part. So now we'll take characters one by one. See if the character is dot, then I just drop my current part to parts and make it empty. And if not, I just add my character to the card. This operation for strings actually in constant time, so you can add the characters to the string in constant time, so it's not a problem. So this is still some linear time code. Not ideal, but still linear time, pretty fast. In the end, so you need to add also the last part. So here I will add p pushback core. Let's check actually. So. Let's check we're still doing everything correctly. Yes. So now I just split this string into separate parts. I believe there is a special function for this in C++. I'm just not that good at C++. That's not a problem. This code is pretty simple. So I go from left to right. Every time I see a dot, I just dump my current string to this vector. So every time I see a dot, I dump another one. I remember all these parts. Now, let's check that we satisfy all the properties. So what's the property we satisfy? First, we need to satisfy the property that number of elements in this array is at least 2. Yeah. Let's say if it is less than 2, I'll put no. Now, let's just check all the properties one by one. Now, we need to check that the first part has length from 1 to 8 and last part has length from 1 to 3. Let's write it like this. Let's check if p0 size is less than 1 or p0 size is greater than 8, and I'll just copy paste. And the last one, let's say number of them. So we check this, we check this. Now check everything in the middle. So it should be from 2 to 11. Nice. So we checked all the properties. Now we know we have at least 2 parts. First part is from 1 to 8, last is from 1 to 3. All the middle parts are from 2 to 11. That's all. Now just output the results. So how do we output the results? Let's just do it like we do here. I'll just go from left to right. Every time I see the split point, I will just split my line to the next line. So let's just do it like this. So I will output. I believe there are many ways to do it. I'll just do it in the most strange way, actually. So I'll just go from left to right and immediately print the result. So I print the first line, then dot. Then I iterate for all lines from 1 to n-1. And I split it like this. Let's count how many we need to split. So if is at least, I just look at this table. Yeah. So if it is at most 9, so if it is at most 9, I want to split my part into left and right parts. So I'll check. So if length is at most 9, I will split it to 1 and something. So x will be length of the first part, let's say, then equals to 1. P size. Yeah. And if not, x will be equal to, let's say, pi size minus 8. So now x is the size of this first part. So I will put this first part. So 0x. Then I change the line. So I'll put this first part. It is the end of the previous file name. Yeah. And then I'll put the second part. From x to pi size, what? Minus x. And then output dot. Okay. So I output first part, split the line, output second part, and dot. Good. And now in the end, I output the last part. Like this. Should work. Yes, I forgot to output yes. Looks okay. Let's submit. So I think the main difficulty of the problem is to implement it carefully. So you need to carefully implement it without any strange corner cases. So I kind of, when I implement it, I think about all possible corner cases and I try to minimize them. Yeah. So first here, I did all possible checks just to make sure I will not have any problems in the future. So I just checked everything possible, which will prevent me to output the correct solution. And then if after that I checked all this, I believe the solution exists. Okay, it will be very painful to have some impossible in the middle of this process. Yeah, so I just check that I have all the conditions satisfied, so my solution exists. I can find it, and then I just find it. So this code is simple. So this code just outputs the solution. Yeah. Yeah. So again, two parts. First, you make all possible checks to make sure that you have a correct you have a solution, and then just construct the solution. So sometimes this part is actually easier than this part. So in problem F, not very standard problem actually, but so the situation is kind of strange, and what we need to do is kind of strange. So what we have, we need to build a grid of like this 2 by 13. And we need to put English letters in all these cells. what I believe what we don't tell you here is you need to put all letters. So you have 26 letters, and you have 26 cells, and you need to put all the letters in there. So you put some permutation of all the letters in these 26 cells. Now, what you need to do? You need to make the given string readable. So you given a string, and you need to make sure that you can read this string as a path in this grid. Not very standard condition. So what does it mean read? So you start in one of the cells, then you move to every time one of the neighboring cells. Yes, and the neighbor if they share a side or a corner. It would be actually fun if you have only side, not corner, but they put it like this. So if you have a side or a corner, there's a neighboring cell, and you make the you walk along this grid, and you need to read the given string, and they promise you that this string has all characters occur in the string at least once, and the length is 27. Again, quite strange problem. So you need to be really careful when you read problem statement, because a lot of small details, each of them actually makes your problem easier. So what we have? So first we have 26 cells, and our string contains all letters at least once. So we need to make sure that our grid contains all the letters. It means we have 26 places for 26 letters. Yeah. So we need to put some permutation. Now the length of the string is 27, and we have 26 letters. It means that almost every letter occurs only once, except one. Yeah. So we have one letter that occurs twice in this string. All other letters occurs once. Let's write this down. So we have a string of size 27. All the characters are unique except one. So one character occurs twice. We have X and X. Now we need somehow to read this whole string. No, if you don't have this extra line, so let's try to solve easier problem. If we don't have this extra X, if we just have a line of size 26. So this line is 27. Yeah. So if we have line of size 26, and we need to read it in this grid, how would you do it? No, easy. So for line 26, you can just put them like this. So you put them here, and then move here, then here, like this. Yeah. So you just arrange all the letters like this. You arrange them in the first row from left to right, then in the second row from right to left. And then you just read any string of size 26. Now, since we have these two letters X here, we need to move to this position X twice. Yeah? So there are multiple ways to do it. Let's do it like this. So let's try to do it. So we'll have first position of X here, let's say. Now I will move to the second line, move here. And here I will make a small jump. I will go here to X and then back here and continue. Then probably X is not in position. So let's shift it somewhere here. Let's do it like here. Yeah. Like this. So I have this cycle. In this cycle, I need to put two positions of X in the correct distance, then I can read both of them here. And then I'll just loop everything to it. Get it? Okay? So that's the plan, at least. That's the plan. How we'll implement this? No. Now again, it's very implementation heavy problem, similar to previous one. Today we have implementation heavy contest. So few times before we have we had several idea heavy problem. Today we have implementation heavy problem. That's nice actually. So I like that we have these diversities. So sometimes we have problems which are hard to solve, problems which are hard to implement. So even if you have the idea of the solution, it's pretty hard to implement it. But it's programming competition. Okay, so sometimes you need to program. Yeah. So now it's kind of clear what solution do we have in mind. Yes. So again, what is the solution? I have these two occurrences of this x. So let's look at this path. So this path between these two x's. I want this path to be here. Yeah. So I'll just put x to the position when the length of this loop equals to distance between these two x's. Yeah. And now I will just arrange everything else. So I arrange this prefix somewhere here, and arrange this suffix. Okay. And arrange this suffix somewhere here. Yeah. Yeah. So solution looks kind of like this. Now you just need to carefully implement this. No, let's go. Oh. Now, imagine you put x in some position here, and the distance to the end equals to, let's say, d. Yeah. So d is position from right to left. So let's just go from right to left. Let's say 0, 1. So this position is d. Yeah. Now, how many steps I can make before I reach the same position d? So I make d steps to the right, then 1 step down, then I can make d steps to the left here. So I can make like here, or I can do it like here. Good. Yeah. So you can make it here. Okay. So if I make it like this, so I make d steps to the right, then d steps to the left. So I have 2 d steps. No, plus 1. Because I step down. Yes. I have d steps to the right, then step down, then d steps to the left. Yes. 2d plus 1. And if I make this longer loop, so I make d steps to the right, 1 step down, d steps to the left, 1 step up. So it will be 2d plus 2. Good. So let's calculate this distance. I need another letter. I used letter D, so let's use letter B. Why not? So this B should be equal to one of these. Yes, and B shouldn't be 0. B cannot be 0. Yes, I cannot make two same letters in a row. So I need to check that B is. Then how to find this D? So this D should be B minus something divided by 2. Now, if you look carefully, then this D should be equal to B minus 1 divided by 2, like this. Let's just implement it one by one. One by one. Really careful. 2. So I take the string. Do they have impossible? Yes, it's possible. Sometimes it's impossible. Okay. It's impossible when I have two same characters in a row. So let's check this. Okay, let's check this. Again, I first check that I have some strange situation, so I don't have to deal with it later. Now, let's find these two characters. So I'll just easy way. So I'll do int is 27 for G I plus 1 27, and just check if they are the same. Yeah. I'll just do it like this. So I need to remember the position and the difference. Okay, let's find this. Okay, let's put this position somewhere. That's x1 and x2. I'll say x1 equals to I, x2 equals to j. Again, this is not the best code, but it will work. Yeah? If you have array of size 27, you can do it as you wish. I can do it in n squared time because I can. It's good. Now, we find these two positions. The positions are x1 and x2. Now, let's just find the difference. Like here, x2 minus x1. And find the value of d. Well, let's just build the result. Let's just build the result. So I will make an array of two strings of size 13. I'll just put dots so it's more visual. Okay. And let's do this. So that's how I will check if I have good. So now let's just build the result like in this picture. So let's put x in correct position. So I will put x in position 0. I need to find position d from the end. So last position is, so I have 13 cells, so I set to 12, so it will 12 minus d. And x is the character in position x1. Let's try this first. Okay, so sometimes it's better not to try to write the whole code at once. So you write some part of the code, check if it's correct. So what I'm here, doesn't look good. Which letter is repeating here? Ah, right. Okay. J. I copied this code. Oh, so letter J is twice. Okay, it's here and here. Looks okay. Now I need to write this middle part between them. Yeah. So let's write this red part between them. So how will do this? So I need to write it here and then here. Many ways to do it actually. So what is the easiest way? Let me think. I think I will do it like this. So I will just fill everything and just skip this x. Yeah? So I start from this point. I will write all the red part, then all the green part, then all the blue part. Yeah? And just skip this second x. So I will start from this position and go in clockwise order, write everything in red part, everything in green part, everything in blue part, and finish here. Let's do it like this. Do it like this. Good. Let's just okay. I try to simplify this solution, but I don't know how. What is the simplest way to do it? So let's remember this starting point. Let's put some k. So k is the index of this position. Yeah. Now I go here, here, and here. So first let's fill the top line. So we'll go for I from k less than 13 I plus plus, and I fill the position 0 I. Yeah. And here I need to find the current element. So current element will be x1. I put the current element and then move to the next element in my string. So we have c equals c plus 1, and I need c plus plus. And then I need to skip it if it equals to this. So if c equals to x2, c plus plus. Not the best code, I don't like it actually. But it should work. Yeah. So I just filled this part. Now I will fill the second part, so from right to left. So I will just go from 12 to 0. And just fill one I. And again, I put the character, move to the next character. So I write this part, and then the iterate part. Let's check we actually missed the second G. So second G was after S, before T. So here. So again, I have S, then G, then T. Yeah, makes sense. And finally, let's finish it. I forgot to go. No, okay. Okay. So if c equals to 27, c equals to, so when I reach the end of the line, I need to move to beginning. I don't like this code at all,
But you can just take it modular 27 or 26.
Oh, makes sense.
And like, I mean, when I have implemented it, I have just written a function that like move to the next position, like next, and then just do one cycle.
Yeah, that's better, but that's actually the better way to do it. So I believe it will also work this way, but yeah, not the best code. I will read your code after that, but I believe it's correct. Again, the main property of the code is to be correct. So if it is, if it passes all the tests, it's actually fine. If you can write code like this and make it pass all the tests, it's good for you. Usually it's better to make the code more clear, then it's easy to debug. But if you're good in debugging, you're probably fine. Yes, okay. So again, at some point you can just write code like this and make it work from the first try. If not, you maybe need to be a little more careful. Let's read your code. Actually, I'm actually interested. Let's check here. Okay. Okay. Long template. Why not? Where's the interesting part? Okay, I don't think it's much better than mine. Yes, okay, so so you have two cases. You have case when you have basically you check a difference, if difference is odd or even.
Yes, okay.
Yeah, but I just do it in the same case. No, it's actually clear enough. Okay, so we just do it. How do you move from point to point? So
the function next. It's like a lambda. It's yes, this one. So just like have implemented it one time and then just while.
So you move around the circle. Really?
Yes.
Makes sense. Good. Strange. I'm kind of tired of this. So I expect this contest to be easier. Maybe I think it's because of a lot of implementation. So I read these problems and I thought they are kind of it's kind of clear what to do in all these problems, but you need to implement a lot. So not the easiest contest. In problem G, okay, so it's a lot of problems like this when you need to sort the array using some strange operations. So it depends on problem. So there are a lot of problems. It's a lot of like area of problems when you need to sort the array using some strange modification. In this problem, the strange modification is you can swap two elements. It's easy, yes. But you can swap only elements if the difference is not difference, but this part. So difference plus 1 is a prime number. No. Okay, if we don't have this property, if we just swap any pair of elements, so how can we sort the sequence? No, sorting the sequence by actually making some permutation. So we need to permute the elements in the correct order, and you can do it in linear time. We don't need to minimize time; we just need some linear time. Yeah. So if we don't have this strange property that this difference must be a prime number, we can just put all numbers in the positions one by one. So we take number 1, put it in position 1, then take number 2, put it in position 2. Yeah? Every time we make one swap. Yeah? So if we don't have this property when we need the difference be prime number, we can put all elements in correct positions in like n minus 1 swaps. Yeah? It's actually true that for some it's in some sense it's the worst case. So it's possible to make permutation when you need to make n minus 1 swaps. Okay. Now we can solve the problem if we allowed to make any swaps. Again, how to do it? You just move the elements to the correct positions from 1 to n. So take first element, put in position 1. Take second element, put in position 2, and so on. Every time you make one swap, you put one element in the correct position. So in n operations, you move all elements to correct positions. Here we only can swap elements if the difference is a prime number. That's kind of strange constraints. So
it's even not a distance. It's something.
It's not distance.
Strange.
The distance plus 1, something. Yeah. No, it's good because if it was distance, you're not allowed to. So here, so if you have only 2 elements, you're not allowed to swap them. So test 2, 1 will be impossible. So they don't want you to have impossible in this situation. So you're allowed to swap neighboring elements at least. That's fun. I'm not sure what is the best plan to. This plan is just to play this a little, and so you kind of. Again, I'm not allowed to make some swaps. I'm allowed only to make swaps for some prime numbers. So I'm allowed to make some swaps. What I need to do if I make one swap which is not allowed? Imagine you have swap of size, let's say 8. So I have element in position 8. I need to put position 1. Yeah, so it's position 8. Position. We'll think, okay, I cannot move elements if the difference plus 1 is 8. Yeah, but I can move them close. I can move them here. Yeah, so this difference plus 1 is 7. Yeah, and this difference is 2. Yeah. So I can swap these elements. So imagine, so here is element x. Yeah. I want to move it to this position. So I can move it in 2 swaps. I swap it here, then swap it here. I think, okay, so problem like this. I need to split kind of element into parts such a way that all these parts are primes. Is it possible to split every element in at most, and you think, okay, you look at the constraint, I have 5 elements. So is it possible to split it into 5 primes? No idea, actually. Maybe, you think, okay? So how to check if it is possible? No, you try, then you have this intuition. You may want to just try. So this actually good way to solve this problem. Again, it's not math competition, it's programming competition. We are programmers, so let's just program and try. So what's the plan? I will try to make all these big jumps using only jumps by prime numbers, and check how many jumps do I actually have. Do I actually need? No, first we need to generate all the primes. We have a lot of work, so let's just do program. Let's read the input. I will not read this before. So I need to generate all the primes. So I have vector. Do we have sieve? Okay, let's have sieve.
Or you just don't want to do like
Hmm?
prime check, like in SQRT time. You don't need like to do it many times, and it's like your local computer. Just like a function that will check it if it's prime or not.
Will it be fast enough?
Like, I mean, if you think that the total number of jumps is 5, then you will check, or like something like that. Then for each element, you will, even if you will go through all elements, it will be still like linear time, because you do it like only 5 times. And then like linear times square t, it's something like normal.
Makes sense. I have 10 power of 5 by SQRT. That should fit into.
And it's like your computer, I mean. You don't have to submit it.
No, but makes sense.
Like, I mean, I have even submitted and it has worked.
Okay. Okay, well, I already started it, so just it's easier for me to write the Artosian sieve because it's easy program. So I will do it anyways because I can. So I will go from 2 to n e plus plus. Then if it's not removed yet, so I add it to array of. So I'll add it to array of primes. And just now just remove everything divisible by this. J equals to I, j less equal n, j plus equal I equal true. Something like this. So
you have forgot to assign it. It should be true at start. Or like we write. Okay, you write it invert way.
Okay. Because it's easy, it's shorter to implement. Yeah. That's basically main reason. So that's basically this simple Artosian sieve that will generate me prime numbers. Now, I need to check. So I will go do it like this. So I'll check all possible steps from 2 to n, and check if I can. How many jumps do I need to do it if I do it greedily? Yeah. So you have this while y is not 0.
1, I guess. Like the problem.
Yeah, because plus 1. Okay. Y is not 1. I make one jump. So I make the maximal possible jump not greater than y. Let's do it using binary search. Because why not? And upper bound minus 1. Okay, let's upper bound. Not greater, yes. And y minus begin minus 1. Not a great code, but should work. Okay, so it is the maximal number which is not greater than that. It's just to say y equals to y minus t plus 1. Yes. Count number of jumps.
I think that salt is not a great idea, because like n will be till 10 to the power of 5. It's just like better to take a maximum value through each. And then just salt it.
Yeah, makes sense.
ZJ should be, and then ZY.
Okay. Second time today. Okay. That's normal. It happens. Not my day. 4. Okay, so finally we have maximal 4 jumps. So it looks promising. So if we just greedily make the maximal possible jumps, we make at most 4 jumps. Yeah. So let's just implement the rest of the solution. So again, we have some hypothesis, we checked it. We don't need to prove it, we just checked it, yeah? And after that, we are quite sure that we know how to solve the problem. So let's solve the problem. Let's finish it.
But is there any normal way to prove it? Like, I mean, for greater numbers.
No,
like, because, like, till 10 to the power of 5, we can say that, like, there will be prime number, like, in logarithm time, and then, like, to check to the logarithm, but, like, if we will have something bigger, is there any normal asymptotic of this stuff?
I'm not sure. All these theorems about prime numbers are kind of complicated, so I'm not sure what is constant 5 response. I believe they put this 5 because they do the same. They check what is the maximal number of jumps. It was 4, and so they put 5 here. I believe that's what happened. What is asymptotical number of maximal jumps you need in this case? I have no idea, actually. So you need in the worst case you need to put in some position so the distance to the closest prime is large. So you need to find the big gap between two consecutive primes.
It's still the log. It's smaller than log, as far as I remember.
No idea. Maybe. I don't know how to prove this. Maybe.
No, I mean, like, me neither, but I mean, I guess that this is what everybody used in all problems, like to the number theory topic.
I'm not as good in number theory, so maybe. So, no idea. So, maybe. But you again, the moral of the story is you don't actually need all these proofs. So if you think something is correct, you can check it instead of trying to prove it. And actually, stress testing or just testing is more. It's better during the contest, because in the contest you can make bug in your proof easily, and then you just assume something is true that's actually not true. But if your stress test is working, it's much better. It tells you that you're much more sure in your hypothesis than if you just prove it. Okay. Let's finish, and then we'll talk. So I'll finish this. So I make the permutation. I make the reverse permutation because do I need it? I'm not sure if I need it. Oh yes, I need to know where all numbers. Now I'll just put all numbers in the correct positions. And plus plus. So I find the position of number I, and I put it to the desired position. So my x is let's see why is Ri is my position minus desired position 0. I don't need this R. And I need to save the result somewhere. And this is so I need to swap elements. Let me check element so +1. I need to swap element I plus y minus 1 and element I plus 1 minus d. Yes, we'll check, and then output result. Like this. Okay, I need left minus. Okay, let's swap them. No, something like this. I forgot to actually swap them. Okay, I need to actually swap them, so I will swap elements in position I plus y minus d and I plus minus r. Okay, and reversed, okay. Not my best code.
And I'm unsure that it will work. Because, like, I mean, in our swap, we affect some different elements. And we can, like, for example, change the position of the elements that we have already placed, for instance. Like, I mean, I'm not sure, but it could be a problem.
What again?
Like, I mean, in our swap, we change positions of, like, we have, like, some help position through which we do our swaps. And after that, we don't put these elements to the back, like, which we have affected. So we have affected some elements, and then they're in some different position. So theoretically, we can affect the elements that we have already placed before, and then, like, this change his place.
But
I'm not sure.
But we only push the elements from right to left. So yes, that's true. So so what we're doing? So I place all the elements in correct positions from right to left. So I always maintain this prefix correct.
Okay, you
Then
maintain the prefix. Okay.
So I put the new element. I move it here. So I only change the positions of all elements I not placed before.
But then you have also to swap the array R, I guess. You have done it. Okay.
I do it like this. I swap elements and they update values in R. So when R is reversed.
Okay, why you just don't do a swap another time? Just function swap one more time.
Also possible. Swaps this and this. Like this. Okay, let's hope it works. So we have final problem to discuss. It's actually a nice problem. Now, no strange algorithms needed, and you just need to think a lot and just explore different cases. So what we have robots. We have a lot of strange parameters for these robots. First parameter is number of robots the robot can carry. So every robot can carry some another robots, and these robots who are carried can carry some another robots. So we can build some tower of robots and stuff like this. And we have some fuel. So we have S liters of fuel, and to fuel the robot we need Fi liters of fuel to make the robot. And we have some strange parameter Li is the distance the robots can travel to. And again, when you read this problem statement a few times, you may think, okay, why do I need this parameter? And the only meaning of this parameter is to check if it is not less than d. So some of this LA are less than d. It means you cannot fuel this robot. This robot has just not enough travel distance to reach the finish. So some robots are basically have Li greater than d or greater or equal to d, and some are less than d. So we have bad robots like a good robot. Okay, so this is the whole meaning of parameter Li. Now we have the parameter, so Fi is amount of fuel and Ci is the number of robots we can put on top of it. Okay, so again, very long statement. You read. I read it basically. I don't remember how many times I read the statement before I actually understand what's going on. So it's like you read it once, you read it twice. After several times you read the statement, you start to understand what's going on. So what's going on? I have some robots. I fuel some of them, and then I put some other robots on top of them. Yeah? So the robots you put on top do not use any fuel. They just move in as passengers. And I can move some robots on top of them and on top of them as well, and so on. So in this, then this whole structure of robots will move to the destination. And I can fuel robot if Li is not 2. Okay, now you start kind of to play this model. So what you can do? So and then you think, okay, but if I have robot, if it's possible to put one robot in another robot. So how called? So if one robot can transport another robot, then why can't I fuel one of them? So you take one robot, fuel them, and then put another robot on top, another robot on top, another robot, and make this tower of robots. Yeah, and just travel to finish. Okay, it looks like, so if robots can carry another robots, you can make with this tower, fuel one robot and move to that. I think, why it's not possible? And you find out that it's not possible because some robots have CI equals to 0. So if CI is equal to 0, this robot can't carry anyone. Yeah. So robot with CI equals 0 looks kind of special. Yeah. So if all CIs are, so if all CI are greater than 0, then solution will always work like this. Yeah. You fuel one of the robots if you have enough fuel to fuel at least one robot. Yeah. And then put all other robots on top and travel to the finish. Now, we solved the problem for special case when you have all positive values of CI. It's good, yeah? So sometimes it's good to think about not the whole problem, but some small sub-problems. So for this case, how would I solve the problem? For this case, solve the problem. Then combine these kind of cases to get the full solution. So we solve the problems if all CI are positive. Now we just need to take care of all CI is equal to 0. So now imagine you put this tower. Yeah? So you have some extra robots with CI equals 0. And think, okay, what can I do with these robots? Well, you can put them on top of this. So some of these robots may carry more than one robot. So yeah. So you have these special places where you can put these useless robots, let's call them, yeah? These robots that not carrying anything. So you have some, let's say, passenger seats here, yeah? So you may take your robots and put them in these positions. What else you can do? If you don't have enough seats here, you can actually fuel some of these robots, yeah? So you can just put fuel in some of these robots and allow them to go to the finish by themselves. That's second option. What else you can do? No, you can do the following. You can fuel one of these robots. So you can take one of these robots, let's say this robot, fuel it, and allow it to go by itself. So we have this combination. So this first part. Then I take this robot and put it as a separate fuel robot. Yeah. So I fuel this robot and fuel this robot. And something here again. Yeah. So I split this tower into 2 towers. If I do it like this, I get one extra spot. So this first spot, this spot. It was first occupied by this robot. Now I fuel this robot. Yeah. So I put them in a separate tower. So I can one extra spot here. And now I have space for one extra robot from this group. So you basically, what I'm doing here, I'm trying to find out what options do I have. What can I do to get more robots in the end? So I can do the following. I can build this tower. It looks like an optimal way. Yeah, it looks like it's never not optimal not to make a tower like this. Yeah? Now I take robots with these robots. These cannot carry anything with C equals to 0. I fuel some of them. So some of them just move them by themselves. Some other I put in these 3 spots. And I can fuel some robots from this part. Yeah. If I fuel robot from this part, I have one extra spot. Good. Now let's see. What will be the answer? What will be the answer? So how many robots can I get in the end? So what I have in the end? I have all robots with CI greater than 0. This all assuming I have at least one robot. So if I fuel at least one robot with CI greater than 0, I can put all of them, all other robots with positive CI on top, and I'm fine. Yeah. So you have this all robots with CI greater than 0. Then so how many of these passenger seats do I have? So in total, so I have all these robots. How many robots can they carry? So we can carry sum of all CI spots. For all CI greater than 0, let's say like this. Yeah. So this is how many spots do I have. Some of them already occupied with another robot, so it will be minus number of robots. Let's say number of robots. Let's see number. CI greater than 0. Yep. So I calculate total number of robots they can carry and subtract number of robots I already have. Yeah. So this will be number of these extra seats for these robots, for these useless robots. They cannot carry anything. Whew. Now now I can fuel some other robots. So I can fuel some robots from here, or I can fuel some robots from here. Every time I put fuel in some robot, I increase number of seats by 1. Yeah. So every time I take robot from here or robot from here, I make 1 extra seat for some another robot. So I increase the result by 1. And I want to maximize the result. Yeah. So what I do? I take all robots with another important part. Doesn't matter which robot you put in the bottom. Yeah. So if you have all positive robots, you take one of them and fuel them, and it doesn't matter which one. Yeah. So you can put any robot as in the bottom as the fuel robot, yes, and put all other robots on top. You will have the same number of empty seats. Yeah. Whew. No, that's it. So now the problem looks like this. Which robots? So now I need to decide which robots to fuel. So I need to fuel at least one robot with positive CI and some other robots. Every robot I fuel give me one extra seat in the end. So I will fuel as many robots as I can, count how many seats do I have in the end, and check how many these robots with 0 C I have. Yeah. And just in the end count how many robots I can get in the end. Whew. Something like this. Also, another option is not to have this. So if you don't have any robots with positive C, so if you don't have any robots which can carry something, then you just fuel some of the robots, and this robot move to the end by themselves. Yeah. In this case, you need to fuel robots with minimal Fi. Yeah. So you pick robots with minimal F, fuel them, move them to the end. That's another option. That's all. So as 2 options. You just pick the maximum of them, and this is your final result. You also need to calculate the minimal amount of fuel, but this will do using binary search in the end. Okay, hope it was clear enough. Let's implement it really quick. Do I have to implement it really quick? Let's try. NDS ND. Okay. Free separate. Okay. So I will do binary search. So I will just put it in the function from the beginning. So I'll just I'll calculate res as calculate. Let's put just as anything nds. Okay. Why I do it like this? I'm too lazy today. Okay, you can do it. F and L. Okay. So I need to also calculate the minimum amount of fuel, so I'll do binary search over amount of fuel in the end. But to do this, I will just go make a function. Int calc, int s. I will just put s here. I'll just remove it from here, so just in case. Good. Now just implement all this stuff. No, let's implement first option, second option, when we don't take anything with, don't put anything on top of anything. So just calculate when we put all robots, fuel some robots, and they go to this to destination by themselves. So let's easy implementation. So I will put all interesting robots. So I take all robots, check if it is at least D, so it's good robot. And put Fi. So I need to care about amount of fuel I need to put. So I put these values F of the robots that can travel to the finish by themselves. Now just greedily take the maximal prefix of some at least S, at most S. I will sort it. Greater than S, then break. That's the rest one. Not ideal code, but it will work. So again, I sort all the values, then go from smallest to largest, and just find the maximal amount I can take so I can fuel all of them and move them to the finish. So this case 1. So this, okay, let's keep it like this. Now, second case, I need to take I need to take at least one robot. At least one robot with positive value of C. So let's find all robots with positive value of C. Okay. I need to find the positive value of C and fuelable. So I need robot if Ci is greater than 0 and it's possible to fuel. So if Li is greater than D. Whew. So over all robots like this, I need to find the one with minimal amount of fuel. I hate this problem already. Okay, why I give you this problem? Because I want to prepare you for strange problems. Yes, that's why. So I check if j equals -1 or if fi is less than fj, j equals I. So I found the minimal value of f over all robots that have positive c and length at least d. Nice. So I found this robot basically. So this robot has index j. Now I will put all other robots that I can fill. So I need to calculate number of seats I have, and put. Okay, let's do it one by one. Let's calculate number of seats I have. Seats, I mean, okay, you got it. Let's say seats. Initially, I have one. No, I have C of j seats. So if j is not -1. Okay, if j equals -1, just return res 1. Also, if I don't have enough fuel, okay, if j -1, or if fj is greater than s, then I have not enough fuel to fuel even one of these. Yeah, okay, nice problem. I love it. Now, so initially I have this amount of okay. See these empty spots when I can put these extra robots. So initially I have one robot with index j and have this amount of robots I can put on top. Now every time if ci is greater than 0, I put it on top. Okay, and not j. I put it on top, so now I have plus ci robots and -1. I use one of the spots and get ci extra spots. Okay. Now I need to count how many 0 robots I have. Okay. You can do it in the same loop. I'll just do it in the sections. Okay. In zeros. If ci equal 0, then 0 plus plus. Let's count these non-zeros as well. Yep. So I count number of non-zero robots, now count number of 0 robots, and count number of empty space. Now I will use the rest of my fuel to fuel some of the robots to increase the amount of seats I have. Yes. So I'll take all the robots. Check if this robot is not j, and I can fill it. So if L equal D, I will put it in array A. I will reuse the same array A. Push back. Then I will do the same part. I'll just copy it from here. Never do it like this. Never do it like this. I sort this array. Okay. Yeah, good enough. So I try to fuel as many robots as I can. Initially, I already fueled robot J. Yeah. So I try to fuel this. Well, F. If I have too much, then break. Increase, and then increase number of seats. Now, my second result will be amount of all non-zero robots plus minimum of number of seats and number of 0 robots. Yes. So I put all non-zero robots here. Then I have some extra seats. I put some 0 robots there. So this is a minimum of number of seats and number of 0 robots. Whew, looks fine. Maximum of res. Will it work or not? What do you think? We have 85 lines of perfect code, I think. Let's try. So we don't output anything. So we found only the first number, but the second number will be much easier. You'll see. 1. Doesn't look correct. Should be 2. I have 10. Oh, yes, I can put this robot. And then I have one spot. I can put one more robot on it. Yes, I can put 2 robots. That's strange. I can even put this robot and this. Ah, no, it has not enough distance. Okay, so I could put this robot with 6 and put some another robot on top. Let's check this part. So it's 0 and is at least D. Looks okay. Why we didn't find it? Yes, we have robot now. It actually looks okay. Why? What? Why we have 0 non-zero robots? Ah, we have 0. Okay, okay, we have to take off this. So we pick this one. Okay, so but we have some 0 robots. We have 1 seat. What? Looks okay. Ah, +1. We have 1 with extra robot. Or we can increase NZ by 1 point. We have start NZ from 0. We count all robots except this starting robot. Okay. Oh. I hate when you have a program, you just need to add +1, and it's actually good. Oh. Good. So we calculate the first number from the output. Let's calculate the second one. So calculate the second one. I will just do a binary search, and it's easy. So you just check. So you put some 2 values. First value is bad value, like so. -1 is not enough fuel. Yes, and
it will not be the time limit because like your solution works right now in log, I guess, and now it will be in log square, or I miss something.
I believe should be fine. No,
okay, because like I mean I have written just in log solution and it wasn't so
that's
hard.
right. No, the only part which works in log is just sorting.
And then okay.
No, everything else is actually linear. So I can remove the sorting actually. You can sort all the arrays from. You can sort all these elements from the beginning, so you don't need this sorting. I'm just too lazy to do it. But yes, you can do it in linear time. I think it will work just like this. We'll check. We will not check because code forces will not judge us today. But I hope it will work. So this is not enough. This is enough. And now, S. This is enough. And now let's see, while R is greater than +1, I will check something in the middle. And just check if getting this amount of fuel give me the same result as before. It means I have enough fuel, so R moved here. If not, I have not enough fuel, so I move L here. So now R is the minimal value which is good. L will be maximum value which is bad. So that my answer will be R. Yeah? Okay, let's just believe it will work magically. we don't have any ways to check, but we will just believe. If it doesn't work, I will record another session when I will fix all the bugs. Okay. Let's read your solution probably. So how you do it?
It's a bit unclear, but hopefully.
Well, I have structure robot. That's actually a good plan. I'm too lazy to do it. If problem a little bit more complicated, I will do it also like this. So instead of having these three separate arrays, you just make a structure when you kind of contain all your important values in the same place. Especially better when you sort them. So when you try to sort these triples, it's better to make structure and sort these structures. And you have not nulls, you have nulls. Okay, so if not nulls, you put it for not nulls. Okay. Yes, and here calculate the amount of free space. Okay, let's be fully plus c and minus 1. Here plus and you kind of do it without binary search or what?
Yeah, like, I mean, I have binary search, but in this, so I mean, I basically brute force or like iterate through the amount of like robot that moves. Like in the beginning, so like I just increase this free place by 1, and then I just using binary search like upper bound, I search how much of null robots we can move.
Makes sense. Yeah, why not? That's another way to do it. Good. I believe you can do something like 2 pointers also, so you can just.
Yeah, I mean, I was too lazy to do it in 2 pointers, because like I mean, nlock or n is this
still should work.
Constraints. It's not a big deal. It wasn't.
Good. Yeah, nice solution, actually, very clear. Good. Oh no, runtimer. Oh, I hate it. How can I get runtimer? Something is empty. How? Here. Okay. Only here. And here probably. No, again? What? I A of size 0. Ah, not n. Okay. Okay, and here. Yes, okay.
Just like a small life hack, you can press Ctrl Shift V and it will open a buffer of all coverage stuff.
Why? What?
Ctrl Shift V.
Wow.
So like I mean, if you have copied something randomly, you can just.
Nice, thank you. You learn everything every day. Nice thing. That's why I have this class, because you actually teach me something every time. Okay. It's actually embarrassing. Okay, we have integer problem. Okay, we have overflow problems everywhere. Okay, let's put everything long. Okay, no, okay, res1 is not long, so. Okay, problem is only with this stable here. So here I calculate sum of all these places. It can be overflown. Okay.
But actually, just curious, what's your opinion on hash define int long?
I usually don't do it because I'm too scared. So I usually okay. So I don't know why I don't never do it. Probably I'm scared I'll have a time limit and I need to change it back everywhere. Probably I just need to do it like this. I don't know. It's like some for historical reasons, I believe. Not this part. I don't know why. Maybe it's time to just to use long everywhere and just forget about these problems. But last time actually in the contest I had problem when I have overflow of 64-bit integers, and that was kind of.
Then just use this like 128 integer. This custom input and output operator.
But then you have problem when you overflow. Another problem I had to use Python because it was even more than so insensitive. So You never guess. But yes, maybe it will solve like 99% of all the problems if I just make define int long like normal people do. I think it comes from because I moved to C++ from Java, and in Java you you don't have defines obviously, and you have to use integers when you indexing arrays.
But wait, like, have you written an CPC in Java? So before all like your comparative programming stuff, you have code in Java or like
Before. So I started programming when I was very young. I programmed in Pascal, and a lot of time I actually competed using Pascal, but it was like 20 years ago. And I won ICPC World Finals in using Pascal, and then Pascal was removed from ICPC and from other competitions. So we moved to Java because of historical reasons. I think in St. Petersburg at that time it was popular to use Java for everything. So we just learned Java, and we knew a lot how Java is working. So we moved to Java, and then actually a long time in my competitive programming career I programmed using Java. I believe I moved Java in 2005, I believe, when we started use Topcoder. It was Topcoder that days. So in Topcoder we participate using Java, and I moved to C++ in some 2015, maybe like 10 years after that.
wow.
So it's because it was just nonsense. You write the same program, and just you have time limit because Java is too slow, and you like do it in every contest. And we just got tired of getting these time limits, so we moved from C++ from Java to C++. And so I have some of my habits moved from Java with me. So I probably need to adjust. Yes, probably it's time to move on. Okay, it's too slow. Wait, so let's believe it will work.
Could you make a contest a bit harder?
Okay, the problem is if contest is too easy, you just limit your time. Just not solve it in 2 hours, or in 3 hours, solve it in 2 hours.
Okay.
You see, like I'm doing it in usually in like 2 hours with all the explanations. So it's possible to do it even faster. So if I don't have to explain it, I believe I can do it in 1 hour or something like this. So just try to do it as fast as you can. It's also good training just to solve the problems as fast as you can. Okay, thank you again. See you next week.